Continuing our discussion of solubility, today we are going to be looking at a graph called a solubility curve, which will tell us how much of a solute can be dissolved in a given amount, or that maximum. And that's related to saturation. If you remember, a saturated solution is the maximum amount of solute that can be dissolved in a solution. When we've reached that amount, it is saturated. And if I were to add more, then it would collect on the bottom. I would have excess. It would no longer be able to be dissolved in that solution. An unsaturated solution has less than that maximum amount of solute dissolved. And these notes here of under the curve and on the curve relate to our solubility curve if you look down at the bottom right. So I have A, B, C, D, E, and F for my different solutes. And for solute A, I'm just going to trace its graph. Actually, I'm going to use a different color so that you can see it a little bit more clearly. So this is going to be a yellow highlighter on my solute A line. And for solute A, if I were to be at, let's say, 40 degrees Celsius, that would be on this part of the line. And let's say I dissolved here under the curve. That looks like it's about 5 grams. This would be an unsaturated solution because I have the possibility to go all the way up to the curve, and the line of A is about halfway, so 10 grams. So my absolute maximum for 40 degrees Celsius is about 10 grams. But if I have 5 grams, I have an unsaturated solution. So saturated is on the line. Anything under the line for that given solute is going to be unsaturated. The third type of saturation is called a supersaturated solution. And this is where we can kind of force in a little extra solute by heating it. It's an unstable solution that eventually will cool down, and then that excess that we forced in will we call it fall out, meaning it will become excess at the bottom as it cools. So a supersaturated solution will not be able to exist for very long. It will only be able to sustain that while its temperature is increased. That leads us to ways we can manipulate the saturation for a time in order to achieve a supersaturated solution. And that includes heating. That's the main way we can do that. But we could also stir the solution, crush the solute, or add more solvent in order to get more solute to dissolve. And again, the solubility curve is the graph that I just showed you, used to determine how much solute will dissolve at a given temperature. So let's start, do some practice with this curve. And like I said before, when we're dealing with a solubility curve, we want to make sure we're looking at the correct curve. So I'm going to color code these really quickly, and you can do that as well if you have some highlighters handy. So I'm going to do just some different highlighting colors. We'll do pink for F. And then we'll do orange for E. We'll do yellow for, it's like I did C there. We'll do green for D. Blue for B, and see, purple for A. So hopefully you can see that a little bit more clearly based on their colors. So using the solubility curve, let's fill in the table. And a couple of things to note about using a solubility curve is that when we are reading one, notice on the y-axis here, we have 100 grams of water as our kind of default amount of water for this solution. So when our first table, it says all of these are in 100 grams of water. So if it's in 100 grams of water, You can read straight from the table. Straight from the graph. And then put it in your table straight from the graph, because 100 grams is the default. So for A at 10 degrees Celsius, let's find 10 degrees, which would be here. My curve looks like it's at about 10 grams, about halfway up the line. So I can make 10 grams dissolve in 100 grams of water at 10 degrees Celsius. If I increase the temperature to 50, now I can force a little bit more in here. It looks like I'm about 3/4 of the way up. That would be 15 grams. And I've made a supersaturated solution from the previous by heating it. So when I heat this up, how much more room is available to dissolve compound A after the solution is heated? Well, once it's heated, I can force in an additional 5 grams. 15 is 5 more than 10. So what would happen if the solution was cooled back down to that 10 degrees Celsius? Well, what would happen was the solution would only be able to hold 10 again, and we would have 5 grams of excess on the bottom. So our solution would go back. Would only hold 10 grams, so we'd have 5 grams excess on the bottom. And again, that's why a supersaturated solution, or one that's been manipulated by heating, is unstable, because as soon as it cools back down, it will just become excess on the bottom. So let's continue reading from the graph our values at these different temperatures. So going to line B, at 10 degrees and at 50 degrees. It looks like at 10 degrees, I'm at about 35 grams. Actually, it's a little over that, maybe 38. Again, we're eyeballing this, so 35 is close enough. I'm going to write 38 because it looks like it's a little bit closer to 40. And then as I increase to 50 degrees, looks like I'm at maybe 39. This one's pretty flat line. The B doesn't change much. C, that's our yellow line, same temperatures here. So it looks like we've got 30 grams on that line. And then when we heat up the temperature to 50, now I can do, it's right on that line of 40. For sample D, that's our green line at 10 degrees. Woo, we're way down here. We can only fit 5 grams of solute D. And when we increase the temperature to 50, we've made quite an increase here, 28 grams. And again, we're just reading straight from the graph at these different temperatures because it's at the default of in 100 grams. For solute E, we're about here, so 55 grams. And 50 degrees, about 75 grams. And then F, it's our pink line down here. About 15 grams can dissolve, and then at 50 degrees, about 75 grams. So there's our amounts that we can dissolve at different temperatures, reading it from each of those graphs. Now, if we adjust the amount of water in our solution, we will want to take what's directly from the graph and kind of use that same ratio. So if I were going to do 50 grams of water, now I'm going to be able to only do half of the amount dissolved because I have half of the solvent. If I have 200 grams of water, now I can do double because I have double the amount of water. So it's going to be proportional to your amount of water. And if it's the same, then it's going to just remain constant. So I did leave us the same compounds at the same temperature, so we can use these numbers and just adjust them by the ratio. So 50, now we're going to have half of our water, so we will be able to dissolve half of what we just found in our table. So half of 10 is 5 grams, and half of 15 is 7.5. You will not find these values on the graph because, again, the graph defaults at 100 grams of water. So you'll need to read it from the graph and then adjust based on how much solvent you have compared to the 100 grams of water. So B is 200. That's going to be double of what we found in the previous table. Doubling your numbers. C is still 100 grams, so that will stay the same. D is in 50 grams of water, so this is half again. We're taking half of those values from the previous table. Then E, this should say 200 grams, it does, so we need to double this from our first table. Okay, and F, 100 grams, same as before. So when you adjust the amount of water, then you need to also adjust by the same ratio of what you read on the table. The table defaults at 100, 50 is half of 100, so your amount of solute that can be dissolved needs to be half of what you would read from the table. And same for 200, then you would need to double. On the back, or on page 11, you have another solubility curve. This time, instead of being labeled A, B, C, and so on, these are actually labeled with the solute chemical formula. So just to be careful on which is which, some of them look very, like the labels are really close. They're all written above their line. So if you just need to kind of identify which is which. And then I would suggest color coding them if you have highlighters or, crayons or something that can help you. It looks like that NaCl line is just a straight line across. That one usually gets confused with the KClO3 line. Students usually get those confused. So it's just kind of like this flat line, sort of like in our previous one, B, kind of like that one. So use the graph to answer these questions, following the same line of thought that we did in our examples.